Hello, everyone, and welcome back to the deep dive. Have you ever looked up at the sun, felt its warmth, and wondered what's really going on inside? Not just the light and heat we get, but the hidden processes. Today, we're digging into a real scientific detective story, one that baffled physicists for decades and, well, ultimately revealed a fundamental secret of the universe.
Yeah, we're talking about solar neutrinos, these incredibly tiny elusive particles that stream right out from the sun's core. For years, there was this big mismatch between theory and what experiments were actually finding. It was called the solar neutrino problem. And we'll trace that journey from the puzzle to a solution that honestly changed physics.
We'll unpack how scientists, using some amazing ingenuity and these giant underground detectors, finally cracked this cosmic case. So get ready for some aha moments, because this is where it gets really interesting. Okay, let's start right there. What exactly are these neutrinos?
Right? Imagine particles,
Mm.
super tiny, neutral, almost no mass. They travel pretty much the speed of light and barely interact with anything. Wolfgang Pauli first proposed they existed way back in 1930. He's trying to figure out some missing energy in radioactive beta decay,
Mm.
where a nucleus changes and spits out an electron. It looked like energy just vanished.
Boom, right.
Yeah. And then Enrico Fermi came along and actually named them neutrinos, like little neutral ones.
Yeah.
But it took, well, over 20 years until Frederick Rains and Clyde Cowan actually detected them in mid-50s. They used a nuclear reactor to prove they were real.
Okay, so they're real but ghostly. How do they connect to the sun? We know it's this giant fusion furnace.
Exactly. Deep inside the sun's core, you've got immense heat, immense pressure. Hydrogen atoms are fusing into helium, mostly through the proton chain, the deep chain, and a bit through the CNO cycle, too.
Mhm.
These reactions release, enormous amounts of energy,
Yeah.
sunlight, and crucially, they also produce just billions and billions of electron neutrinos every single second.
Billions. Wow.
And here's the amazing part. Those neutrinos are the only things made in the core that get out immediately. They just zip right through the sun, reach Earth in about 8 minutes. So they're like direct messengers, straight from the sun's heart.
That sounds like the perfect way to actually see inside the sun then. So scientists thought, let's build detectors.
Precisely. That was the drive. In the late 1960s, you had the first really big attempt. A chemist, Raymond Davis Jr., worked with John Bockall, a physicist. Bockall developed the standard solar model, the SSM, which predicted how many neutrinos the sun should be making. And Davis set up the Homestake experiment way down in a gold mine in South Dakota.
A gold mine. Okay, tell us about this neutrino trap. It sounds intense.
Oh, it absolutely was. Think about this. Davis used a huge tank filled with 100,000 gallons of tetrachloroethylene.
I assume cleaning fluid, right?
Right. Basically dry cleaning fluids full of chlorine-37 atoms. The idea was when an electron neutrino with enough energy, over 0.81 MeV, hit a chlorine atom, it would change it into a radioactive argon-37 atom. Just a few atoms. Then they had to chemically extract that tiny amount of argon and count it.
Wait, count individual atoms?
Yes.
In 100,000 gallons?
Exactly. It was like finding maybe a few dozen specific atoms in a pool containing like 10 to the power of 30 atoms. Unbelievably difficult. And it was mostly sensitive to these higher energy neutrinos called 8B neutrinos.
Okay, so what did this incredible experiment find?
Well, the first results came out in 1968, and they were frankly startling. Davis found only about 1/3. Some calculations said even less, maybe under 20% of the neutrinos Bockall's model predicted. And boom, right there you have it, the solar neutrino problem.
1/3 or less. So huge debate time. Was the sun model wrong? Was the experiment off? Or something else entirely?
Exactly. It threw everything into question. For years, people argued, is our understanding of the sun wrong? Or is Davis's really unusual experiment maybe missing something? Both options had huge implications,
But the Homestake results held up, didn't they? They kept measuring.
They did. Davis ran that experiment for decades, and the deficit just stayed there. It was real. So that pushed for new experiments, different techniques, looking at different neutrino energies to try and figure this out.
Okay, so what came next? Who else joined the hunt?
Well, over in Japan, Masatoshi Koshiba led the Kamiokande experiment. It started in '83. It was actually first built to look for something else, proton decay, but they upgraded it for solar neutrinos. This was different. It was a huge tank of water, 2,340 tons deep underground, a water Cherenkov detector.
Water Cherenkov. And you mentioned this was a game changer, neutrino astronomy.
Precisely. Kamiokande gave us the first real-time directional detection. That was huge. Around 1988, it saw the Cherenkov light like a tiny flash of light when a neutrino knocked an electron in the water.
Like an optical sonic boom.
Sort of, yeah. And because they could see the direction of the flash, they could confirm the neutrinos were definitely coming from the sun, and they could measure their energy. The results, again, a deficit. They saw about half the predicted 8B neutrinos. So Kushiba's work really launched neutrino astronomy, direction, timing, energy. Much richer data.
Okay, so the problem's still there, confirmed by a totally different method. What else? Any other approaches?
In the early 90s, 2 more experiments came online using gallium. There was SAGE in Russia and GALX, which later became GNO in Italy. These were sensitive to much lower energy neutrinos, including the PP neutrinos, the most common type from the sun, down to 0.233 MeV.
And they found
A deficit, too. Not quite as dramatic as home stakes, maybe closer to the 50% mark like Kamiokande, but still definitely fewer than expected. So by the mid-90s, you had multiple experiments, different techniques, different energy ranges, all seeing fewer solar neutrinos than the models predicted.
the evidence was really piling up. It seemed less likely it was just the sun model being wrong. So physicists started thinking about the neutrinos themselves.
Exactly. That's when older, kind of radical ideas started getting serious attention. Back in 1969, Bruno Pontecorvo had suggested something revolutionary. What if neutrinos could change their type, their flavor, on the way from the sun?
Flavor change. Okay, this sounds wild. What does that mean?
Well, we know neutrinos come in 3 types, or flavors:
Yeah.
electron, muon, and tau. The sun only makes electron neutrinos in its core fusion reactions. Pontecorvo's idea, neutrino oscillation, was, what if those electron neutrinos could spontaneously morph into muon or tau neutrinos during their journey? Our detectors back then were mostly built to see electron neutrinos.
Ah, so if they changed flavor.
We wouldn't see them. They would be missing, just disguised as a different flavor.
Okay, but that idea, oscillation, it had a huge implication.
Massive.
Yeah.
For neutrinos to oscillate, to change flavor, they must have mass,
Yeah.
and the standard model of particle physics at the time assumed neutrinos were massless, like photons.
So this wasn't just tweaking the model, it was adding something fundamentally new.
Totally. It required physics beyond the standard model.
And then there was this matter effect, too.
Right. Building on Pontecorvo's idea, Wolfenstein, and later Mikheyev and Smirnov, figured out something else. They realized that this oscillation, this flavor change, could actually be enhanced, speeded up, as neutrinos pass through the incredibly dense matter inside the sun. This became known as the MSW effect.
Okay.
And it helped explain why the deficit seemed different for different energy neutrinos. Higher energy ones might change flavor more efficiently inside the sun. So now you had a really compelling theoretical explanation for everything seen so far. The stage was set for a definitive test.
So a solid theory, but needing that crucial proof. What was the experiment or experiments that finally provided the smoking gun?
It really came down to 2 major players around the turn of the millennium: Super Kamiokande in Japan, the successor to Kamiokande, and the Sudbury Neutrino Observatory, SNO, in Canada.
Super K. Bigger and better than Kamiokande.
Oh, absolutely. Starting in 96, Super Kamiokande was just enormous. 50,000 tons of ultra-pure water.
50,000 tons.
Yeah, about 30 times bigger than the original. Lined with over 11,000 incredibly sensitive light detectors. It gave much more precise measurements of those 8B neutrinos, confirming the deficit with really high accuracy. Vital data.
But SNO was the one that really cracked the flavor mystery, right? How did it do that?
SNO was unique. It was located even deeper underground, about 2 kilometers, in a mine near Sudbury. It used 1,000 tons of heavy water D2O, deuterium oxide. That heavy water was the key, because it allowed SNO to detect solar neutrinos using 3 different reactions. 2 were absolutely crucial.
Okay, what were they?
First, a charged current reaction, or CC. This reaction could only happen with electron neutrinos, so it counted just the electron flavor arriving from the sun. Second, a neutral current reaction, or NC. This one was special. It was equally sensitive to all 3 active flavors: electron, muon, and tau.
Wait, so SNO could count just the electron neutrinos with one reaction?
Yep.
And then count the total number of all types of neutrinos with the other reaction?
Exactly. That was the genius of it. It could measure the electron neutrino flux and independently measure the total neutrino flux.
That is brilliant. It's like checking if any fish changed color on the way to the net.
Precisely. And the results, announced in 2001, were the breakthrough. SNO found that the number of electron neutrinos, the CC rate, was definitely low, just like everyone else had seen, confirmed the deficit. But the total number of neutrinos, the NC rate, matched the predictions from the standard solar model perfectly.
Ah, so the total number was right all along. The neutrinos weren't actually missing.
They were just in disguise. The electron neutrinos that seemed to vanish had simply changed into muon and tau neutrinos on their way here. SNO proved it. independent of the solar model details. That was the definitive evidence for neutrino oscillation.
Wow. Just wow. Case closed.
Pretty much. Combined with Super K's precision measurements and later results from the CAMLAND experiment looking at reactive neutrinos, it sealed the deal. Neutrinos have mass. They oscillate. Physics beyond the standard model was real.
What an incredible scientific triumph. Years of work by so many people.
Absolutely monumental. And recognized, too. Raymond Davis Jr. and Masatoshi Koshiba share the Nobel Prize in Physics in 2002 for their pioneering work. And then in 2015, Arthur McDonald from SNO and Takaaki Kajita from Super Kamiokande got the Nobel for the discovery of neutrino oscillations. It was a fantastic story.
An amazing resolution. But, science never really stops, does it? Solving one big problem often just points to new questions. So, what were the big takeaways, and where has solar neutrino research gone since then?
Well, the fundamental takeaways were huge. Neutrinos change flavor, which means they must have mass. That's big news for particle physics. The MSW effect, how matter influences this change, seems to be correct. And importantly, our models of the sun, the standard solar models, were actually pretty good. The sun was making the right number of neutrinos. They were just changing en route.
Okay, so the sun model was okay, but neutrinos were weirder than we thought. What puzzles are left? What's next?
Well, the field is still incredibly active. One major ongoing issue is the solar metallicity problem.
Metallicity? Like metals in the sun?
Yeah, basically the abundance of elements heavier than hydrogen and helium. Newer ways of measuring the sun's surface suggest it has fewer heavy elements, lower metallicity than older estimates. The trouble is, if you plug those lower metallicity values into the solar models, they don't match up well with observations from helioseismology.
Helioseismology, like listening to the sun ring like a bell.
Exactly, studying the sound waves traveling through it. So there's this tension. Spectroscopy suggests low metallicity. Helioseismology fits better with higher metallicity. It affects how we model the sun's core temperature and structure.
Okay, a new puzzle. How can our tiny neutrino friends help with that?
Well, remember the CNO cycle. That's secondary fusion process in the sun.
Right, using carbon, nitrogen, oxygen.
Exactly. The rate of that cycle, and thus the number of CNO neutrinos produced, is very sensitive to the amount of carbon, nitrogen, and oxygen right in the sun's core. It's a direct probe of the core's metallicity. So precisely measuring CNO neutrinos could tell us which metallicity model is closer to the truth deep inside. The Borexino experiment in Italy, using a different technique with liquid scintillator, has been key here. It made the first direct detections of the low-energy PP neutrinos, and more recently, the CNO neutrinos. Big steps.
So using neutrinos to probe the sun's composition, what other secrets are we still trying to uncover with them?
We're pushing for more precision on the neutrino properties themselves, like what are their exact masses? We only know the differences between them. What's the absolute scale? And how are the masses ordered? Is it a normal or inverted hierarchy? Which mixing parameters are still uncertain. Solar neutrinos provide unique information, especially for certain mixing angles and mass differences. Plus, people are looking for more exotic things, like do neutrinos have weird interactions as they go through the sun or Earth? Do they have a tiny magnetic moment? Any deviation could point to new physics.
It really sounds like the sun is just this incredible ongoing laboratory for fundamental physics.
It absolutely is. And the experiments keep getting bigger and better. Hyperkamiokande is being built now even bigger than Super K. It'll give amazing precision. SNO Plus is the successor to SNO, using liquid scintillator now, focusing on low-energy stuff in CNO. And Chinese detectors like JNO in China will also contribute. We're trying to push the precision frontier, looking for those tiny effects that might signal the next revolution in physics.
What an amazing story. From this baffling puzzle, this deficit, to completely changing our view of fundamental particles.
It really is a classic example of how science works. An astrophysical mystery drove discoveries in particle physics. It showed our sun model was mostly right, but revealed this whole new world of neutrino mass and mixing, forcing us to go beyond the original standard model. It highlights how sometimes the most progress comes from investigating those little things that don't quite fit.
So for you listening, I think the takeaway is that even when a big scientific problem gets solved, it doesn't just end there. It often opens up completely new avenues, deeper questions, and even more exciting science.
Think about it. Our sun isn't just a big ball of light. It's this dynamic cosmic lab. And it's constantly sending us these tiny messengers, neutrinos, that tell us not just about the sun itself, but about the fundamental rules of matter and energy. The humble neutrino, once a ghost, is still very much at the frontier of discovery.
Well, we hope you enjoyed diving deep with us into the fascinating world of solar neutrinos.